Thank you. So my name's Kevin Den Wymelenberg. I am relatively new at University of Oregon. Before that was at University of Idaho for about 11 years, and before that was at UW. I run a lab called the Energy Studies and Buildings Lab, so my focus on the talk today is going to be with an energy emphasis. It's my bread and butter work. I'm not a wood scientist. I am an architect by training, learned to speak engineer over time, and mostly concerned about creating beautiful buildings for people to live, work, and play within, and do it in a manner that will allow us to thrive for a very long time without having to build new power plants. We're really blessed in the Pacific Northwest with an abundance of relatively green power with our hydro resource. Roughly speaking, depending on your jurisdiction, anywhere from 50, maybe 90% in some jurisdictions of our electricity comes from this really clean, renewable resource, notwithstanding salmon implications, as all things have trickle effects. But I really want to talk about how energy and wood buildings can have some synergies, and how there are also some challenges that we need to overcome. So the big emphasis is going to be this conversation of thermal mass. And when we talk about thermal mass in buildings, the sort of go-to resource is concrete, right? And we know in our net zero energy buildings, one of the most consistent strategies that we employ to achieve these really low internal loads is a high thermal mass building, so that we can do night flush cooling and get through the peak cooling hours the next hot summer afternoon, because we've stored all that cool energy from the nighttime in our mass, typically in our concrete floors, right? So this is the challenge that we have to overcome if we want to do net zero energy buildings from an operational energy standpoint. I think that picks up well on Professor Simonen's talk, but also do and find ways to achieve those carbon sequestration benefits of doing more wood in buildings. So my goal of the talk is really to get my arms around how big of a problem is this, and is it achievable? And if so, what are the steps we need to do to get there? So I'm talking in a session on overall building systems, overall integrated building systems. This is a little diagram that my predecessor, Charlie Brown, did, and it's looking at a classroom prototype, and you get a sense of all the various things we're considering. We're looking at heat gain and heat loss out of a skylight. We're looking at the daylight availability from that skylight. We're doing some funny things to bounce the daylight around and try to soften it with this little cloud. We've got some ceiling fans providing airflow for increased perceived cooling. And then, of course, we are tracking our ambient air temperature. We're tracking our mass temperature. There's some strategies in here. We see the little squiggly arrows. Those are suggesting we're doing some night flush cooling of mass, kind of how I set up the talk. So that's where we're headed. Here's another building before I jump into that case study. This is another example of a really low or high surface to floor area ratio, really thin building. It's about cross ventilation, and we're making a lot of painful steps to think about getting airflow pathways and the right amount of surface area to cool off at night. So a lot of floors and ceilings covered with concrete, with very little trying to get between us and that access to that mass, setting up this possibility of a comfortable radiant field. So I include those slides to see there's a lot of integrated steps that I'm going to focus today mostly on the amount of mass. And then this one here, I want to draw your attention to the amount of airflow. So we think of a window for fresh air. You think about kind of that much airflow, this little hopper window down at the bottom. But if you want to do night flush cooling of mass, you need a much more abundant amount of airflow. So we're designing systems in like this, where we've got dampers and louvers that have doors to swing for airtight during the summer or during the winter, but open up for more airflow at night in the summer. Really quickly, 1 CFM of air is the amount that we need to kind of one person to breathe and have the right amount of oxygen. 15 CFM is how much we need to get the sort of smells out of the space. About 300 CFM will have that perceived cooling benefit, but to do the night flush of mass and exhaust all that heat that's built up over the day, we're looking at roughly 600 CFM. So we need a lot of airflow, and we also need a lot of access to mass. This is the potential, and it's very much driven by loads inside the building. So I'll come back to this theme. We want to reduce our internal loads. But this is Salem's climate, actually, and what we're looking at is 24 hours on the vertical axis, 12 months of the year on the horizontal, and it says we can completely design a building without mechanical cooling if we're down at that 50 BTU per square foot range in terms of internal heat load. But if we creep up to the 150, we're starting to have days shown in white that we need to install mechanical cooling systems. And you can see how relatively expensive those systems are for how little of the year we really have to run them. And of course, if we're designing higher internal load buildings, maybe 250 BTU per square foot, we're going to see a lot more demand on our cooling system. So we need to reduce loads to even have this conversation in the first place. So I'm going to start with this as an assumption of the 150. And I'm going to look at a little classroom building that we did just near Salem. And this is the Theological Studies building. It's kind of fun. I'll show you these little turbine ventilators are one of those things that we can do to drive more airflow through the building, even with just the slightest amount of wind. So those guys are all on the back side of these classrooms here. You see a large skylight, trying to make sure we don't have to turn more loads on by turning electric lights on over the course of the day. So I'm going to take you through a 900 square foot classroom. It looks like this guy. This is a very prototypical classroom. It happens to be for maybe a non-prototypical use here. It's actually the monks are studying here about theology. And a little diagram of what we're trying to get done. So that same cartoon I was talking about. We've got some motorized dampers up here for automated night flush of inlet of air. We've got some manual windows and manual dampers if the persons during the daytime want more airflow through the space. And then we've got a lot of exposed, in this case, concrete here on the floor and on the inboard wall. So this is the hallway. Turbine ventilator, skylight, and lighting controls to make sure the lights are off. Just another example. And we did build this building with no mechanical cooling. So this has really got to work. Airflow studies to show the outdoor temperature and the indoor temperature over the course of the day. You see at the top bar, we're looking at the night before. And the building is now unoccupied. And you can see the bar here. The outdoor temperature is around 85 degrees Fahrenheit, indoors at about 70. We know that with ceiling fans and exposed thermal mass that's cool, we can let that ambient air temperature in the room drift up much above what you might consider normal for a typical ambient air temperature that you might put on your thermostat in your home. You say maybe you want 74 degrees on the wall in your home, but in a high mass building with night flush, you can let that drift up to 80, 82 because of the perceived comfort benefits. So what we're looking at is a peak cooling design day here at 9 p.m. where we've opened up all those inlets and we're letting that fresh air from outdoor in through these lower and upper windows and driving it out the turbine. We see whether there's wind or not, it works because we're relying on stack effect. So even here with no wind at 10 p.m., we're still getting cooling effect, and that interior temperature has really dropped down. It's still a little above the outdoor temp, 65 outdoors, 67 indoors, and creeping through the course of the day, and we see how those track, and then we go into closed mode, and we'll see that the indoor temperature stays pretty stable, 76, but the outdoor is going up to a design day in Salem of about 90 degrees. Maintaining comfort indoors. So this is our goal, and then of course we start it all over again the next day. You can see some of the people in the room are creating these little plumes of heat, and then it goes to unoccupied mode. Those are real data from a course of a day. You just have to trust me. It's working. The good news is that this internal mass temp is not drifting up, and the outdoor temp is swinging wildly, but the indoor ambient air and perceived comfort are in the comfort range. These guys are happy. Okay, so here's the polemic, right? That's all based on a whole lot of concrete. So what do we do if we're looking at wood? I'm going to come back to this slide in a moment. The case study building is looking at a 900 square foot classroom, 150 BTUs per square foot per day of load. We're looking at a 4-inch concrete topping slab. This is the case study sort of base load assumptions, and a couple other things about efficiency and whatnot, about the cooling system efficiency. So 150 BTU per square foot, we're counting on 6 inches in this base case, concrete slab, and we're looking at 2.5 times the floor area ratio to achieve the cooling potential. So that means we don't need any mechanical cooling. What happens if we go all CLT everywhere? And I'll talk a little bit about some of my assumptions here underneath the hood if you're interested. But we realize that if we want to have just all CLT everywhere, we need to design a building that's 1/3 of that already very low internal heat gain. So your target is 50 BTU per square foot if you want to achieve it all with the thermal mass from the CLT alone. If we want to look at the 150 BTU load, the more realistic load, we're talking about a theoretically impossible answer. 7 times the floor area as available exposed CLT. We can't do it. If we want to talk about a concrete screed on top of 4-inch slab on the floor with 6-inch CLTs as structure and ceiling and walls, we're looking at 5 times the floor area. Still really not conceivable. You get about 3.5. That's what you have access to when you take out some area for doors and skylights and things like that work against you. So we need to get down to 3.5. Here's a solution that gets us there, and it shows that we can design a cooling load at about 112 BTUs per square foot. So still 50 or 30% less than an already very aggressive, energy efficient, almost net zero type building. So the good news there, I think, is it's in the ballpark, but we need to get very, very aggressive on our loads if we want to talk about this. I also have a sub-theme going on throughout here, which I'm not going to pick up for sake of time, about embodied energy, which would be the steel and concrete industry version versus the carbon story, which would be the wood industry version in Professor Simonen's words. And of course, we want both, right? So we want the carbon story and the operational energy story. One thing we're working on right now with Professor Maria Paula from OSU, who's in the room, is the Smart CLT project. And there's a couple other professors included, Andre Barbosa as well. And a couple of the things that we're looking at as a starting point, we all have our own interests bringing to the bear. Hopefully you've seen from my presentation, I'm interested in the operational energy performance and then the interior comfort of our occupants in these ultra-low energy solutions. So we're looking at post-occupancy thermal and energy performance. We're looking at acoustics performance, vibrational comfort, and really the first phase of the research is to try to find a very low-cost, reliable, embedded sensor network that we can leave in buildings to ensure that we're meeting the target performance of our design intent, but also to make sure that we can learn what's working, what's not working, so we can do this better as we move forward in the future. All right, that's my bit. Thanks a lot.